In this tutorial, we will look at how to calibrate and optimize a motor using the oscilloscope and the controller configuration window. As we have previously seen, the system allows for the tuning of 3 control loops: position, velocity, and current. Specifically, the current loop is calibrated during production alongside the encoder. Therefore, today we will focus exclusively on optimizing the motor's velocity and position loops. We begin with the first acquisition via the oscilloscope. The motor is moving between 2 points using a polynomial profile, configured with an acceleration time of 200 milliseconds and a dwell time of 150 milliseconds. The interface displays the 4 standard signals: target position, feedback position, target velocity, and feedback velocity. After starting the acquisition, we wait for the traces to be transferred from the motor to the NiLAB starter interface to analyze the data. The goal of effective tuning is to minimize 2 critical errors: velocity following error and position following error. Once the acquisition is complete, we split the channels to observe the details more clearly. We can immediately notice that the system is not calibrated at all, as there is a significant lag between the target and feedback signals. We will now proceed with the velocity loop calibration. We set channels 1 and 2 to display the velocity profiles and channels 3 and 4 to show the difference between them, the velocity following error. We start the acquisition again and wait for the transfer to complete. Looking at the new acquisition, we notice a very high following error. To correct this offset, we open the control configurator window and increase the velocity gain from 500 to 1500. After downloading the data to the motor, we reacquire the signals and wait for the transfer. Now the signals are beginning to track more closely, and the error has already been halved. Let's increase the value further to 3000 and download again. The traces are now almost perfectly overlapped, and the error has been significantly reduced. As for the velocity integral, we will keep it at 10 for now, a standard value that can be increased for high dynamic applications, where even stricter tracking is required. Now, let's move on to the position loop. We fix the channels to display the target, and feedback position profiles, and reacquire the signals. At this stage, we have a fundamental tool at our disposal, velocity feed forward, which serves to minimize the lag between the theoretical and actual curves. Currently, the error is significant, as seen by the gap between the two traces. The first step is to increase the position gain from 50 to 80. While this intervention would already reduce the error, for an optimal result, we will activate the feed forward, initially setting it to 10. We then reacquire the signals. With this new parameter, the curves tend to overlap, and the error drops drastically below 1 mm. We further refine the value by increasing it to 15, and verify the result by reacquiring the signals. The signals are now virtually identical, and the following error has been further reduced across almost the entire movement dynamic. Once this level of precision is reached, we can consider the tuning successful. It is important to remember that the final calibration must always be performed with the actual load mounted and in accordance with the intended duty cycle. Finally, to make these settings permanent and ensure they are not lost at power off, go to the Parameters window and click Write Configuration to flash to store the values within the motor.